So thanks to the organizers for the kind invitation, and thanks to everybody for joining on this Friday afternoon. Indeed, so this is what I would like to talk about, hypersimplices, which is a certain kind of polytope, tropical geometry, and finite metric spaces. So it's a lot of new stuff, which is current ongoing work with my PhD student Laura Casabella from Leipzig and a postdoc in Berlin, Lars Kastner. The others are referred to older work of mine with various other people that you kind of serve for context. You'll see their names later. All right, so that's the plan. I would like to talk about this special class of polytopes called hypersimplices and explain a little bit what their role in tropical geometry is. And my main result will be a computational one. And my main job for this presentation will be to convince you that this is a meaningful computation. And one of the ingredients to make it meaningful is the subject of finite metric spaces, which has a long history and an interesting overlap with algorithmic biology, for instance, phylogenetic trees, and you'll see some of that. All right, so hypersimplices and their subdivisions, or decompositions, as it was called in Nick's talk in the morning. So his decompositions are my subdivisions. So what is this about? Well, I think for a conference which has formal power series in its title, it is adequate to start with formal power series. And so this thing C, what is it? C curly braces twice T. So this is the field of formal Puiseux series with complex coefficients. So this is formal power series with rational exponents and an extra condition, which is not so important because the examples that you see here are not so impressive. So my power series are just mere monomials in this parameter t, but you could think of more involved power series here. So everything that I'm doing would work with those. And what am I doing? I'm taking a matrix out of those coefficients. In this example, it's a 2×5 matrix. And I'm interested in the row span of this matrix. So this is a 2-dimensional linear subspace and a 5-dimensional vector space over the field of Puiseux series. And I'm interested in its tropicalization. How does this work? Well, so one way to think about this is in terms of Plücker coordinates. And so the first step then would be to produce the ordinary Plücker vector, which is formed from the maximal minors of this matrix. Right, so I have a 2×5 matrix. The maximal minors are given by 2×2 matrices and their determinants. And I have these 5 columns. So I have 5 choose 2 means 10, many of those. And so I get 10 elements in my field of choice. And this gives this Plücker vector. Now, the tropicalization does the following. It throws away most of the information and only keeps the lower degree. Right? So just so that we are on the same page, so just to do one example, if I look at the first 2 columns of this matrix, then the determinant is 5 times t to the 8 plus 2 times t to the 5. And I'm interested in the lowest degree, which in this particular case is 5. And so this is how I get the first entry of this vector. And then for the 9 remaining maximum minors, I get the remaining coordinates. Of course, the particular vector depends on the choice in which I label my minors. All right. So this is a tropicalized Plücker vector. So these are interesting in tropical geometry. In a way, you could argue that they stood at the cradle of tropical geometry as we know it today, because there is a celebrated paper of Speyer and Sturmfels, which I would like to summarize here now. So first of all, so they gave the definition of the tropical Grassmannian. That's also the title of that paper. For the purpose of this talk, it is good enough to think about it as a set of all these tropicalized Plücker vectors for given parameters k and n. And let me just say, so k is at least 2 and at most n½ rounded down in this talk. And so this is the tropical Grassmannian as a set. It does carry a fan structure which comes from Gröbner bases, but let me sweep this under the rug, so it's not so important for today. And the main result of Speyer and Sturmfels is, from that paper, that this tropical Grassmannian arises in a systematic way from a known and beloved algebraic variety, the ordinary Grassmannian, which parameterizes the k-dimensional subspaces of an n-dimensional vector space. And then ever since then, and so these things have numerous applications in tropical geometry and outside, and therefore it was a main goal to kind of explain them as good as we can, and this includes explicit computations. And in that several times mentioned paper by Speyer and Sturmfels, they already provide the data for the case where k equals 3 and n equals 6. And they also explain how these things work for k equals 2 and arbitrary n. So for the purpose, so then there are just 2 more computational results known. So these 3, 6 and these 2 n cases kind of can be done by hand. But none of the other things can be done by hand. So there's a joint paper with Sven Hermann, Anders Jensen, Bernd Sturmfels from 2009, so where we computed the tropical Grassmannian for 3.7, and a few years later, so this year, a team of researchers in computer algebra and tropical geometry was able to settle the next case 3.8. Okay, which was a massive computer algebra experiment. Now, yeah.
So what do you really mean by settle this case?
Oh, so the goal is to compute these tropical Grassmannians explicitly for as many values of k and n that you can do. Right? So the explicit description of the tropical Grassmannian for the various parameters is a meaningful goal, and for these cases that I'm writing down, so this has been achieved. Yeah.
Is it relevant that those are the Grassmannians of finite cluster type?
Not so much. I mean, there's a little bit of relationship to cluster algebras, but not for the purpose of this talk today. Okay. So, I mean, thinking about other Coxeter groups and their things, so like symplectic cases, so is that your question?
No, I mean, that once you go to 3.9, the Grassmannian's still there, it's cluster variety, but now it's not finite type. These are exactly the ones that were as a cluster variety, it's a finite type.
Yeah, but that's just a coincidence. So this is just because they are the smallest ones, and so the sheer size is the limiting factor. It's not a. That is true. So this is related to cluster algebras, if you like. That's right. Yes, that's right. I will come back to this a little bit later. Okay, so now in the title of this talk, so there were these hypersimplices, and I mentioned these subdivisions, and I would like to spend a moment to explain that. It's a little bit unfortunate. Okay, so the hypersimplex, I give you 2 descriptions. So one's in terms of equations and inequalities, which is the one on the top of the title. So it is given as the set of points in the 0, 1 cube, so all the coordinates range between 0 and 1, and we have one extra condition, which is sum of the coordinates equals k. So it's a slice of the unit cube. That's the outer description of this polytope, and the inner description in terms of vertices, it's the convex hull of those 0, 1 vectors of length n with exactly k ones. And so here's the first non-trivial example for k equals 2 and n equals 4. So this is a regular octahedron sitting in 4-dimensional space in the hyperplane sum of the coordinates equals 2. So you might observe that the vertices correspond bijectively to the basis of the uniform matroid U24, and this is the general case. for these hypersimplices. So these are matroid polytopes, as in Nick's talk in the morning. And so matroid theory won't play a role for the purpose of this presentation, but if you love matroids, you can get more mileage out of what I'll be telling you if you specialize or generalize everything that I'm doing here for an arbitrary matroid-based polytope of your choosing. So I will stick to the uniform case, but you can do this way more generally. So such a Plücker vector that you saw for k and n can be read as a height function of the set of vertices, or the equivalently the basis, which means, so the points, the vertices are points in n-dimensional space, and then I add one more coordinate which comes from this tropical Plücker vector. I take the convex hull in the space one dimension higher, and then I look at the thing from below, and I project it back, and what I get is a regular subdivision. It's a special kind of a decomposition that you saw before. And here's an example. For instance, if I take this octahedron, just imagine that all the red points are lifted to height 0, so then they live in a hyperplane, and the one remaining point, which is marked blue, is lifted to height 1, right? So then this hypersimplex, this octahedron breaks into 2 Egyptian pyramids, and so this is what you get in this case, and this is actually an example which comes from such a tropical Plücker vector, and this is the same subdivision, coincidentally, that Nick started his talk also out with, right? So 2 Egyptian pyramids sharing this central quadrangle. And it turns out that the cells that you obtain are matroid-based polytopes. So the cells correspond to matroids. Now, the object that I'm interested in most for the purpose of this talk is the secondary fan of a given polytope, or more generally a point configuration, which, when I talk about a polytope, means the point configuration formed by the vertices of that polytope. So whenever I have a subdivision or decomposition of my polytope, I can ask which vectors, which height functions induce that particular subdivision, if any. Right? So there are also non-regular subdivisions, so those which do not come about in this way. But if they do, I can then often there's more than one vector, because once I have one, for instance, I can scale it by an arbitrary positive scalar, and then it will induce the same subdivision. Or if I have 2 different ones, I can add them. And from this you can see, and still they induce the same subdivision. So from this you can see that the set of all those height functions inducing a fixed subdivision, unless it is empty, is a relatively open polyhedral cone. And this is a secondary cone. These secondary cones fit together nicely. They form a fan, and this is the secondary fan. These are typically unwieldy and large objects, but in this case, for this octahedron, I can explain this, and this is the image on the lower right. Right? So let me just explain this slowly. So we have 6 vertices, so these height functions live in R to the 6, 1 dimension per vertex of my polytope. But if I'm only interested in these height functions, then I have many, many height functions inducing the same. I started to explain this, but there's also a 4-dimensional space of linealities in my fan, which just comes from choosing an affine basis. So for instance, if I have a height function inducing a subdivision, then I can add the all ones vector to the height function, and then I still induce the same subdivision. And then there are more things that I can do. So in order to get rid of this this lineality space of the secondary fan, I can pick an affine basis, which, if the polytope is 3-dimensional, has 4 points, and therefore, effectively, the actually interesting object lives in the quotient R to the 6 divided by R to the 4 for the 4 choices of the 4 vectors of the affine basis, and 6 minus 4 is 2, so the relevant part of the information is a 2-dimensional polyhedral fan, and this is the picture that you see here. So in the middle, so this is the 0 point, and then this subdivision that you saw here corresponds to a one-dimensional, to a ray of the subdivision pointing upwards. And then there are two more symmetric choices. So they correspond to the three ways to split the octahedron into these pairs of Egyptian pyramids. And then if you overlay any two of those, then you get a triangulation around a choice of a diagonal. Again, I tried to sketch one example. If you overlay this thing and this thing, then you get a triangulation. And here are the two symmetric pictures. And all together, this is how a secondary fan looks like. And as you can also see here, in order to I could draw the picture even more efficiently, I can visualize a fan by intersecting with the unit sphere of the respective space. So then I would just have a circle and three isolated points for these rays. So this is about the information that is contained in this thing. Okay, that is obviously a toy example. Let us move to the next case. Now, k is still equal to 2, so this is my most interesting case for the entire talk, k equals 2. But n increases by 1, so now n is 5. Then this is so the red part is a picture that you will find in many sources. So this is a picture how this tropical Grassmannian looks like for these parameters 2 and 5. And I need to go back one. I forgot to explain one thing. So inside this secondary fan, I can look for those subdivisions which have the property as I indicated here for the tropical Plücker vectors. So I just take those subdivisions where each cell corresponds to a matroid, and so these form the Dressian. Okay, and so this is I'm only mentioning this because this is a subfan of this secondary fan. In particular, it does have a fan structure, and by construction, it contains the tropical Grassmannian as a set. And sometimes, in particular in the case when k equals 2, so then the tropical Grassmannian and this Dressian always coincide. So that's the fan structure that you will see. I said this before. In general, the tropical Grassmannian has another complicated fan structure that I don't want to mess with because I'm focusing on k equals 2. And in this case, these two fan structures agree. Now, so turns out that this tropical Grassmannian is two-dimensional. It's a two-dimensional fan, modulo linearities. Again, I can intersect with the unit sphere in that respective space. So I get a one-dimensional spherical polytopic complex. Also, so therefore I can draw it as a graph. And this is this red thing which looks like the Peterson graph that you see here. So this is an image of the tropical Grassmannian in some unit sphere, in some two-dimensional unit sphere in 10-dimensional ambient space. This is how this looks like. And then everything that you see around tries to visualize how this tropical Grassmannian sits inside this secondary fan. So this is a little bit difficult to draw because I'm still in 10-dimensional space. I need to subtract 5 dimensions for the linearity space, still makes 5. So I'm looking for a two-dimensional thing which sits inside a 5-dimensional thing, so which means it is tiny. But this picture only takes this 5-dimensional fan and intersects it and just considers the two skeleton. Only the two skeleton, again, I intersect with the unit sphere, therefore I get another graph, and this is what you see in this picture. So what you should realize from this picture is that, well, while this red thing is tiny, tiny, tiny inside, it's two-dimensional in this large 5-dimensional thing, but it is very well connected. Everything in the outside the red thing is super close to the red thing because it is connected to many of these vertices. This is kind of the inspiration of everything that we are doing. So one of the motivation of this work is to try to understand this embedding of this tropical Grassmannian into the secondary fan, and so this picture gives you an idea. All right, so Now, this is kind of the main result of this talk. So this is so if we talk about the hypersimplex for k equals 2 and n equals 7, so then it turns out that it has exactly 153 billion regular triangulations in about 30 million orbits, and and these orbits come from the natural operation of the symmetric group of degree 7, which operates on the 7 space dimensions. And then, I have subsets of cardinality 7, and then it permutes those sets accordingly because I don't change the size. And it turns out, so it has exactly 13,000 and something orbits of regular courses subdivisions. So these correspond, regular courses subdivisions are those subdivisions which correspond to these rays, right? If I go back to this case of the octahedron, so then the corresponding number would be 3. 3 for these 3 ways to chop up this Egyptian pyramid. And then, so the 3 are symmetric, so there's only 1 orbit. So this is the previous case. So I showed you the case n equals 4. I showed you the case n equals 5. This case that I was skipping is this case n equals 6, and this was done by Josephine and Bernd Sturmfels in 2004. Okay, I will mention their result more precisely a little bit later. Okay, so first of all, what kind of result is this, right? So the thing is, it's just a corollary of a way more complicated result. So the actual result is the full description of this secondary fan. You can download it if you wish from Zenodo. So it is described how this works, and this is compressed data, and the total size is about 1 gigabyte of data. Right, so just to put this into perspective, so one of the notoriously long and important papers of the 20th century, it's an important result in group theory due to Veit and Thompson about from the 1960s, which says that every finite group of odd order is solvable. This is notorious because it has a long proof. So this is 250 pages in the Pacific Journal. And so if you look up the PDF file, so then this is about 500 kilobytes. So this is only the statement of this theorem, and this is 2,000 times larger. So this is it's a massively large result. And so of course we need to discuss why this should be useful. And this will be the rest of this talk, that I would like to convince you that it is worthwhile to do such a thing. And this funny statement with these precise numbers is just about the only thing that you can write down in a paper to be read by human beings. Okay? So this is just the shadow of the shadow of the shadow of the actual result. Yeah, so this is a very good question. So how large is the proof? Well, what's the proof? So the proof consists of the code for the software plus the description. So, but the size of the proof is negligible this is just a few dozen megabytes more. But so the statement is the largest part, Frank.
Well, perhaps more interesting is what were the resources needed to do this computation?
Very good question. That's a very good question. So
You should repeat my question.
Yeah, so sorry. So the question was, so what kind of resources were needed to obtain this result? In fact, we did this computation several times in the first, and every iteration led to an improvement of the implementation. In the first attempt, it took about 100 days. In the second attempt, it took about 10 days. And in the final attempt, less than a day. Yet not... Exactly. I was leaving this to the end. Yes, not on your pocket calculator. It was on a massive cluster with 256 cores with a lot of RAM. Okay, so the fastest thing that we have is 256 times 10. So let's say around about 3,000 CPU hours. on a fairly large computer. But so this is doable. But there's one important thing is, so the methods got better on the way. So we used the computation of these large exults to sharpen our tools. Okay, but this was only a side outcome. Let me talk a few moments about, and we also computed the 3.6 case, but I will not explain this for this talk. I promise to stick to the case k equals 2. Let me talk a little bit about software experiments of this kind. So the first that I'm aware of for computing secondary fans goes back to Jesus de Loera's PhD thesis, where he produced this program Puntos written in Maple, which is a little bit of a proof of concept implementation, and the first industrial strength implementation was by Jörg Rambau. So these years, so 2023 doesn't mean that Topcom is deceased. So this is just, 2002 was the year of the first version, and 2023 is the year of the last version, which was published. And the software that we used is our own, which is called MP Topcom, because it shares one ingredient with Jörg's code, but otherwise it's independent. In particular, it's massively parallel. This is what MP means. And it uses a lot of Polymax stuff. All right, so, but the computation was done with our own software. Of course, there are valid questions concerning the validity of such results and what you should do in order to convince other people that this is actually correct. Let me ignore this for the moment. Let me just point out so that we thought about this quite a bit. And there is an ongoing effort in Germany about research data in mathematics in general. And so this consortium produced a white paper which just says something about how you should organize such computations. And we followed those rules. And if you want to, are you interested in specific things to computer algebra, which is maybe of interest to this community, then with Lars Kastner and Benjamin Lorenz, we wrote a chapter in the forthcoming book on the new software system OSCAR about this thing. Okay, but let me not discuss this for the moment. You can ask questions later. So let's just work with the result that we have. So the question is, to what extent is such a thing useful? And I will give you two and a half answers to this. So here's my first answer. So looking at this data, we were able to recognize patterns from this data, which led to conjectures, which led to results that you can prove by hand. Okay, so this is just the tip of the iceberg. We have several more. Let me just show you one of them. So there's a very specific way to write a lifting function on this hypersimplex. It's not very complicated, quite to the contrary. So you order the vertices in a specific way, right? So lexicographically, where the first coordinate is the largest. And so this is why the first vector in the sequence for k equals 2 and n equals 5 is this vector 1, 1, 0, 0. And the last one is 0, 1, 1. And the remaining are come in between. And so this particular height function just takes the first n minus k of these vectors, 2 in this example, and lifts them to height 1. And the remaining one are not lifted at all, meaning they are lifted to height 0. Okay, and then it turns out that you can prove without further need of a computer that the induced subdivision by this height function on the hypersimplex 2n, right? So I wrote it there for arbitrary k. We also have some results for arbitrary k, but I told you several times I'm most interested in the case k equals 2. And in k equals 2, you obtain a coarse subdivision, again, something that corresponds to these rays. And it is not so large. Which means, so this comes with, there's this word spread that occurs here. Whenever you have a polyhedral subdivision, you can just count how many cells you have of maximal dimension, and then that size is the spread. And so the spread in this example is n. If I go back to my very first example with this Egyptian pyramids in the octahedron, right? So the octahedron is chopped up into 2 Egyptian pyramids, so which means the spread is 2 in this case. Okay, and so this is the spread is n. Why is this relevant? Well, there are many other subdivisions which much larger spread. And so there's an interesting result of David Speier on tropical linear spaces, which again specializing to the k equals 2 case means if I have a subdivision where each cell is a matroid, right? Matroid polytopes are big, which means you can't have too many of them at the same time. Therefore, that spread is limited and very precisely by the number of n minus 2. So just by knowing that the spread exceeds this number, I already know cannot be a matroidal subdivision. So it is something in the secondary fan outside the tropical Grassmannian. This is what I'm looking for, right? So the philosophy is the tropical Grassmannian is known for k equals 2. And so therefore I'm looking stuff in outside, but I want to have stuff which is not too far away. And so too far away can be measured either combinatorially or metrically. So the metrical thing will come up later, but combinatorially I would like to measure this in terms of the spread. So if I have subdivisions which are near the Dressian, which has cells which are large, therefore there are only few of them, then if I go not too far away, I should not have too many cells there either. So I'm particularly interested in those. And so from this computation, we were able to detect a pattern, and then we could prove this by hand. And we have a couple of more. So this is the first thing. So now, those among you who believe in techniques from artificial intelligence should feel invited to wade through our 1 gigabyte of data and to maybe find other patterns and to recognize more of those courses subdivisions. That would be something that I would find interesting. All right, so you could go along these lines a little bit further, but instead I would like to change to a different topic now. So I already told you, so one reason why we are interested in this computation that we did was we wanted to understand this interaction between this tropical Grassmannian and this surrounding space, this secondary fan. And so analyzing these courses subdivisions is the way, because these are much fewer than these subdivisions in the which are generic, right? So you see this here. So we have these 153 billion guys in 30 million orbits, but we only have these 13,000 types of regular subdivision. So this is super condensed information about a super large object. And this is the kind of information that we want to compute and exploit. And so here's one way that was derived from this computation. Now, suppose that you don't like tropical geometry because you already had enough of this week, or you didn't like it in the first place. Here's another reason why you might be interested in this computation. Okay, let's start from scratch. So suppose you just have endpoints somewhere, abstract points, and you just want to measure distances in some way, in a very crude way. You just have a dissimilarity map which just assigns pairwise distances. The only thing that I'm assuming is that it is non-negative and it is symmetric. And whenever you have this, then I call it a dissimilarity map. This is obviously connected to the topic of before, because those pairs of points can be interpreted as vertices of this hypersimplex, delta 2n, right? So I just write down the sum of the two standard basis vectors which correspond to those entries, and I get a vertex. And then the dissimilarity map assigns a height. Now here's a small technical thing. I rather work with a negative of d, but this is a technical thing. It just depends on lower convex hulls or upper convex hulls. There's no a priori choice. When I prepared the talk in the beginning, I thought I would cheat a little bit and I would save you all the science. But then I had a second thought, namely all the standard software tools use this default Therefore also our data is aligned to the negative of D in this way. So if you want to connect this to the actual data that I showed you before, then you need this sign. But it's just a convention. And so then there is a polyhedron that you can produce, an unbounded polyhedron, which lives in the positive orthant, where I take the sum of two variables, x and xi plus xj, and I ask it to be at least as large as the distance in terms of this dissimilarity map of I and j. You will see an example on the next slide. And then there's another concept, the tight span, which is just the complex of bounded cells. Again, you will see this here. Just, I was talking about the regular subdivision before, and so this is just an explicit construction of a dual of this subdivision, and I'll show this in a minute. There's a theorem about this, and this theorem explains in which sense these tropical Grassmannians are known for the case k equals 2. The way that I chose to phrase this theorem just lumps together the language from three different papers, namely a very old paper of Isbell, and then its rediscovery by Dress 20 years later. And then I combine this with the tropical geometry version of Speyer and Sturmfels. But so it is important to understand in the terms of the history of the subject, this is one of these many results which precedes tropical geometry as we know it. So it was originally phrased in a different language, but now it ties in with a more general theory. And this says, well, if I take such a dissimilarity map, I go through this polyhedral construction, and then this polyhedral complex, this tight span, so this is a tree on n-labeled leaves if and only if the negative of the dissimilarity map is a point in the tropical Grassmannian 2n. All right, so here's the construction with an example. It is tiny, 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 but it's the only example that I can draw in its entirety. So suppose you have just 3 points, and their distances are as given. So the distance between 1 and 2 is 2.5, the distance between 1 and 3 is 3, and the distance between 2 and 3 is 3.5, and then of course symmetrically extended, and the distance of each point to itself is 0. So this is my example, and then I can produce this envelope, this lower envelope. This is this E. This is this unbounded polyhedron in free space. This is this yellow guy. It's sitting in the positive orthant. It's unbounded in all the positive coordinate directions, and so it has all kinds of faces, unbounded ones and bounded ones. And there are 4 vertices. These are marked in white. And then 3 edges, and so it is easy to see that whenever you have a polyhedron and you have a subcomplex of bounded faces, either it is empty if the polyhedron is not pointed, but if it is not empty, then it must be contractible. So here you have a one-dimensional contractible complex, also known as a tree. Okay, this is not a coincidence. You can even go further. You can recover the distances, and then you see how a tree-like metric works, right? So I told you the distance between 1 and 2, so this was part of our input data is 2.5, and this tree explains why, because 2.5 is 1, which is the distance from 1 to the central point, plus 1.5, which is then the distance to the node labeled 2. So this is a polyhedral way to reconstruct the tree from this thing. Of course, there are many other ways. Neighbor joining is the standard algorithm used in biology, for instance. So this is a polyhedral way to explain this construction. Okay, so this tight span is this one-dimensional polyhedral complexes, and I can assign these length, and I can recover this from this construction. Last definition that I need, and then we can I can go to the remaining results. So we need to talk about splits. So whenever I have an n element subset, and I take a non-trivial subset, so neither empty nor the full set, call it A, then I can produce a very cheap dissimilarity function by just assigning zeros and ones for the pairs of points I and j, just depending on if one sits in A and the other one sits in the complement, then I say they are at distance 1. And if they are in the same partition of two elements, then I consider them equal and I call their distance 0. So this is a split dissimilarity. Of course, there's some symmetry going on, and sometimes when I talk about this entire orbit of these split dissimilarities, I just write down their cardinalities. And then if I take such a dissimilarity and do exactly the construction that I showed you before, then I will always get a tree, and a very particular kind of tree, namely a tree with exactly one interior edge. This is this edge that you see over here, and then you have altogether 5 labeled leaves, because 5 was the number of points that I started out with, and then the ones that I was choosing for the set A consist of 1 and 3 and 5, so they sit on one side of this bounded edge, and 2 and 4, which live in the complement, they live on the other side of this thing. So this is a split tree. And so this is how this polyhedral construction looks like for this particular kind of things. So now, okay, so these things are examples which live on the tropical Grassmannian. So here you see this Petersen graph again, so which is the tropical Grassmannian 2-5. And now what I'm putting down is kind of coordinates for this, right? So the nodes correspond to coarsest subdivisions. So all these elements are trees. So what are the coarsest kind of trees? So these are exactly these split trees with exactly one interior edge. And then just a partition into 2 parts of all the labeled leaves that I have. And so this is the tree. So on the upper right, so this is the tree that you just saw before. And so now this guy corresponds to this node. So this tree, because the leaves 1, 3, and 5 live on one side of the bounded edge, 2 and 4 in the complement live on the other side. So this is this tree. Here you see another split tree. So they look the same, but they are labeled differently. And then on the edge between these two nodes, you see a generic tree, which is kind of an overlay of these two split trees. And so this looks like this, right? So passing from this most degenerate situation to a more less degenerate situation, in this example means to take these 3 guys and to resolve this node of degree 4 into 2 nodes of degree 3 each, with a new interior edge in the middle, where this edge in the middle comes from this split tree on the other end of the edge. Okay, so this is how this tropical Grassmannian works. And so this is a general fact. So the coarsest subdivisions of this tropical Grassmannians 2n always correspond to these split trees. Okay, now when you have so of course, a dissimilarity map is a very weak thing. So if you want to impose more structure, so a natural thing to ask for is the triangle inequality. I don't ask for definiteness, so I am allowing for positive distances for points to itself, so schizophrenic points if you wish. This is a pseudometric if the triangle inequality is satisfied. And then you can look for all the dissimilarity maps which satisfy the triangle inequalities, and this is how you get the metric cone. So again, this has been subject to computational scrutiny. There's a long sequence of works in particular by Michel Desarts and Mathieu Dutour-Sikerich, and I'm just summarizing sequences of results. And so the precise numbers are not so important. So the only thing that I would like to point out, so this is also, it's a major computational effort. Now, I'm interested in polyhedral fans, and from these secondary cones that I explained, right? So I have a regular subdivision. I lump together all the height functions giving me the same subdivision. That's the secondary cone. I can intersect them with a metric fan, with a metric cone, and then I get a metric cone of that height function. Again, I get a polyhedral fan. So this is just the secondary fan intersected with a positive orthant, and then it is not so difficult to understand how this works. So the rays of this polyhedral fan are just the negatives, just because I'm always interpreting dissimilarity maps as height functions by passing to the negative. So negative of rays of the secondary fan. And then I have one additional orbit corresponding to the linearity space, which is also occurs as this splitting of one label from all the remaining ones. So this is a result which is essentially known, but it has never been really written up as it seems, and therefore in some of the published papers there are some subtle errors where they are sometimes off by one in a count just because of this second extra orbit that is sometimes ignored. So work on these metric fans and these metric cones has been done by Kuhn, Moulton, and Tönges, who were also motivated by questions in biology. And so in this sense, the computational result that I showed you about the computation of the secondary fan, right, has an immediate corollary. So it also gives you the metric fan. And so in particular, so we had 13,147 rays in the previous case for the secondary fan, and by intersecting with the positive orthant, we pick up one more ray, one more orbit of rays, and again with respect to the symmetric group of degree 7. And this is another outcome of our computation. Why is it so? Is it interesting? Well, other people worked on similar things before. Again, Josephine and Bernd were already mentioned. So they accomplished the same thing for the previous example for the metric fan of points on metric spaces on 6 points. Right, so it's a kind of a combinatorial classification, and now we extend this to 7 points after 20 years, thanks to a massive computation. In the remaining 2 minutes or so, I would like to convince you that this can be used in practice. So these kind of techniques have been applied, so this analysis of metric spaces, to data, for instance, which comes from biology. So here's an example where you have fragments of DNA sequences of 6 types of bees, right? And you measure a distance by writing them aligned. This is a topic in itself, how to do this. And then essentially you count the positions in which they differ. This is how you get a distance function among these 6 types of bees, and this particular data set that I'm processing now comes from the software package Splitstree written by Husen and Bryant. And this defines a dissimilarity map, which I will call beta, so which is just a dissimilarity on 6 points. And so there's in this business, so here's a theorem due to Bundelt and Dress, which marked the beginning of this theory to analyze these dissimilarity maps and just to check to what extent they fit to trees. I showed you, if you have a dissimilarity map which comes from a tree, how to give back the tree. But the important thing is that this polyhedral destruction is continuous in the parameters that you have. You always get a bounded subcomplex, and therefore you can always view this tight span as the space of all the possible trees that you could assign to this data. So this was Dress's intuition, and he provided a geometric way to explain how to process an arbitrary dissimilarity map, and namely you just somehow compare with all these splits, with all these trees with just one internal edge. For each one, you cook up a coefficient, you subtract that, and you get a rest. And how this works in detail, this is what the split theorem is about. And once you apply this, then this particular software that I mentioned produces these pictures, which is a polyhedral complex. It's actually a zonotopal complex, which resembles all possible trees that you could fit those data. And in this particular example, there is only noise except for one relationship between two kinds of bees, and that's the point of this example, because the snippets of DNA strands were just chosen to be artificially short, right? So in a naive way, you can start out with any data set and you want to reconstruct a tree, but that's a little bit naive, and so this is a better description of this. And so this technique can be generalized to arbitrary set of rays of the metric fan. Then you get a more complicated description of a tight span. The important thing here is that you have this pentagon sitting there. From this you can see that you cannot come from a zonotopal complex. So you actually get more information. And so if you look at this now, at this data, you compute all these coefficients that I showed you on the previous slide for all the rays which are involved. So then the analysis of bundled and dress and followers so only concerns everything related to a split. So these are these things with spread 2. And with the technique that we are showing, we are able to explain what is going on in this next thing. And then you can see that everything below is only noise. So the noise is 6 orders of magnitude smaller than everything above. Okay, so this gives you a way to analyze these data sets. And so this is my last slide. So I try to convince you that computing just one large data set of this type gives you insight into constructing courses subdivisions to study embeddings of tropical grassmannians, gives you a classification of finite metric spaces on 7 points, and better resolution for analyzing real-world data. Thank you.
Are there questions for the speaker?
Yeah, if I had time.
Repeat the question.
Yeah. Yeah, so the question was what these coherency indices are. So there's a systematic way how to compute these coefficients, and this is the formula. Okay, I can explain it over a cup of coffee, or should I do it now? Yeah, it takes a few minutes. Yeah, it takes a few minutes to pass. Let me explain this later in private, okay? But there wasn't. So the thing is, there's a systematic way to compute these coefficients. If you only look at splits, then it does not depend on the ordering, but for our generalizations, it does. Okay. But the same formula works.
So you have a very large things which has been computed by software you have somehow to trust. Do you think it would be feasible to somehow certify such kind of software to have consider the result as something proved?
Yeah, of course, that would be my dream, absolutely. We tried to experiment with this a little bit. I talked to several lean developers over the last few weeks and months. I cannot declare victory yet, but it's absolutely on my mind. I'm afraid I'm currently not aware how to do this entirely because everything involved is too large for current lean efforts, as it seems. But we are working on it.
So the quantity of code which is needed.
Yes.
You have a rough idea of how many lines of code. I mean, not the proof, the basic code.
I understand. So the thing is, the code is parallel code. It's not so bad. It's maybe 10,000 lines of code or something like that. but it rests on a number of libraries, and in particular complicated libraries for parallel programming and running supercomputers. And I have no idea how I should certify any of that. Because for some of this is commercial software for which I don't even have the source code. So it's a very complicated question. I'm thinking about it. If you have suggestions, I'm listening.
Other questions?
So you talked about computing the secondary band 2.7, but what about how the couples of Grassmannian fits inside of it? You didn't mention anything about that.
Not very much, yes. So I said, my way of doing this analysis is as follows. So we use this result of David Spire, which limits the spread of everything which is on the Grassmannian. And so therefore we specifically search for coarses subdivisions of low spread, because they are most likely to be close to the Grassmannian, and in many cases we could certify this. But this is an ongoing project. We only have partial information, but that's the intuition. You look for coarses subdivisions, which are kind of manageable, up to symmetry only 13,000, and then you look at those which have a low spread, just a little bit more than n plus 2, something like that, and then you analyze those, and this is what we want to use to study this embedding.
But would it be computationally feasible to compute the pair of the tropical Grassmannian sitting inside of the secondary band?
For 3.7, kind of yes. For 3.8, this was also done, but this was a terrible computation. This required a special computer plus special software, which is not publicly available. I mean, so the parallelization part of the software, that is just a result which came out this year. But so we have access to the data, but it's too fresh. We were not able to process it yet, but that's the plan. Yeah, but these are the only examples that you can work with. We have 3 examples, 3.6, 3.7, 3.8, and everything from 2. So my philosophy is we need to go back to the k equals 2 case, because that is the one that we can compute best with.
Are there other questions? If not, let's thank the speaker.